Hey everyone, back again. Okay, today we are on to Immanuel Kant's Metaphysical Foundations of Natural Science. But before you listen to this, you should probably check out the episode I released, or maybe you're listening to this years ago, but an episode I just released relative to today, titled Immanuel Kant's Prolegomena. What is wrong with me? Prolegomena to any future metaphysics. I think will supply you with a very important kind of foundation to understand what Kant is going to be doing in this text. So go listen to that first. And if you have gone to listen to it, you should know who I am. But in case you're stubborn and did not go listen to it, I'm David. I explain philosophical concepts and ideas and ways to make them accessible to you. So if you're new here, you can like, share, subscribe. That'd be cool. Tell your friends. If you found this as a podcast, you can find it on YouTube where there are sometimes videos. If you found this on YouTube, you can find it as a podcast where there shouldn't be ads or anything. You can just download it. It'll be yours. You can listen to it whenever you like. Apparently, I have a soothing voice. Not right now because I'm coming in hot. But maybe it'll help you fall asleep into that blissful oblivion. Hopefully. That'd be nice. Sleep is great. If you want to contribute to me, don't. Instead, contribute to any Palestinian family that you can find on a GoFundMe or Palestinian organization would be very great if you could do that instead. I would really appreciate it. Yeah, all right, let's just jump into it. This is Immanuel Kant. This guy writes about stuff. Let's see what he's writing about in this book. Starting with the preface. Well, actually, let me reread the title. Metaphysical Foundations of Natural Science, starting with the preface. Now, nature has there's two ways to understand nature. Either we can think of it as a thing's constitution or its essence, like the nature of myself, human nature, that kind of thing. Or we think of nature as the totality of all things. That is everything. Everything technically falls under the realm of nature, which is always, I know this is a total side point, not relevant at all to what we're discussing, but you know those people who are all about like natural, and they avoid chemicals, etc., as though chemicals are not themselves natural. Like, of course, they take a certain kind of human intervention and kind of to produce these synthetic chemicals that may otherwise not have appeared in nature. But like, have you ever walked through nature and seen a loaf of bread just sprouting up from the ground? I mean, in order to make bread, it takes human intervention in the mixing of chemicals. Anyways, total side point. What he's referring to here is nature in terms of everything. Everything. Well, the entirety of the universe and all the things within it and all the little physical laws that they follow. Now, the reason he's focused on this and not the first definition, where the first definition just looks at like an individual's nature or the nature of like a species, is that you can't really form a science from it in the same way as you can with the other stuff, because it's going to depend on the creature you're looking at or the person. It's going to be different from person to person. That is their nature. And so science can only be found when we look at the totality of all things in this sense. So science, that is in the sense that it is possible with the second definition, that is referring to everything, the totality of all things, it must account for two parts of that nature. That is, it must account for the part attuned to outer sense and the part attuned to inner sense. These are the body and the soul, respectively. Now, he doesn't mean soul here in terms of like any kind of spiritual thing. I mean, in part, he kind of does. But he's referring to that like inner sense of self with which you have an ongoing kind of relationship and dialogue with yourself, that shapes your kind of attunement to the world. So in the case of his conversation of space and time, which he says that space and time aren't found out there in the universe, but instead are the expressions of the human capacity and desire for like experiencing things sequentially in terms of cause and effect. You know, I'm being very short about this. Go check out the other episodes if you want more. But he adds a point to that. He adds the point that space refers and really belongs to the capacity for experience in the outer world that is outside of ourselves. Because it is within, and time works out there as well, but like it is only with the existence of space as the expression of, you know, transcendental aesthetic, as he puts it, not the expression of the transcendental aesthetic, but like it is the sensible expression of our whatever intuition or something. But space is required for us to be able to tell one object from another in the world. That is, we need space to be able to tell when an object ends and another begins, even though this raises a number of questions that we're going to get into in this book, actually. Like, what is space? How do we measure space? Does it really exist? Et cetera, et cetera. Whereas time, he says, it does exist out there, but it is just a narrative kind of imposed upon things, more or less, in order to understand their sequential movements in the world in accordance with the synthetic a priori understanding of cause and effect that is universal, yet nevertheless we don't see it all the time. We don't see every single effect produced by a cause. You know, we can only infer from seeing a few causes and a few effects that it is a universal unchanging principle of the universe. Now, time is reserved, though, not only for the outer world, but for the inner world as well, in our minds. So if you were to think of a chair, that chair is not taking up any space in your mind. However, it must be taking up something that is, in order for us to experience it as even as an image in our mind's eye, which is just speculation, but still like is part of experience, we are experiencing that thing not along the axis of space, but instead along the axis of time. So when you put an object in your mind that you think of it, you are experiencing it in time, not in space. So the only way you can experience it there is by having it occupy a kind of duration or a length of time in your mind. So space and time then work in this way to speak to the outer world and the inner world. So a natural science tries to find, or the metaphysics of a natural science, metaphysical foundations of a natural science, looks at the qualities that make the experience of nature possible. Now, if you've heard this and you listen to the other episode, you might think we're just going to be talking about the exact same stuff we had before. We are not. We're going to be talking about physics a lot more now. We're going to be talking about how Kant was a genius, how Kant was Einstein before Einstein, with obviously not to the same extent, but he's going to be talking about, and this book was written in the late 18th century, like 1780s. He wrote this, essentially being like, yeah, everything's relative. Space is configured not in itself, but instead by the relative subject position of the person viewing it. I mean, these are, Kant was making all of these claims. He also gets some stuff wrong, which one of the most amazing things about this book is that he pursues some of the most interesting, like, physical and astronomical. He pursues some of these ideas just by using his system that he developed with the critique of pure reason, critique of practical reason, etc. With that system, he was able to infer a number of things about the universe, about space, about time, about relativity, etc., way before those things became popularized in like scientific understanding. He showed the actual merits of his philosophical project in furnishing us with ways to understand the world and universe. So the laws of nature have to be cognized a priori for him. That is, in order for them to be a science, they have to be applicable everywhere and not just like localized, which is one of the fundamental problems of like math and physics, is that, you know, we do have laws, but like, let's say if you were somebody who worked with water and there are laws that pertain to water, but you never end up really dealing with water in the perfect conditions in which the laws perfectly apply. So when people are actually dealing with water, perhaps they're trying to design how wide a ravine should be under that goes under a bridge or something, in order to maintain the integrity of the bridge, not make it too wide. There's a lot of things you're going to have to factor in, from like the strength of the soil to the presence of rocks to the flow of the river, etc., etc. You can use laws and stuff to provide a lot of really important groundwork, which is exactly what he's going to try to do here with natural science and metaphysics. But it still requires a lot of like kind of specific uncovering of that area and what's going on there that you can't just explain with universal laws. So these laws they're never like all encompassing, but they do provide the important and necessary foundations to understand how something like water works, how the flow of how movement works, how physics works. And it's for this reason he makes a funny point. He's like, chemistry isn't a science. And it's funny because chemistry is like, it just depends always on the chemical. Like, it's hard to come up with universal principles about like chemistry. I know that there's, not that I know anything about chemistry, there are probably some general principles of chemistry, like how you can add chemicals and in a certain like mathematical type formula that might be applicable all the time. I don't know. But the thing with chemicals is like, it kind of just depends on quantities, on what the chemical is, how it's reacting with another one, anything like that. So he's like, for that reason, you can't have a science of chemistry, but it's funny. So what we are after here are pure ideas, pure natural laws pertaining to the natural sciences, pertaining to nature, in order to furnish us, to provide us with science. But it's like a tricky thing because we have to look at the physical world, which is often comprised of various different phenomena, different things moving at different speeds, different spaces, etc., etc. And it is from there that we must try to extract certain universal principles, which he's going to try and supply us here. So insofar as natural science is pure, that is, natural science tries to furnish us, I keep using the word furnish, but whatever, natural science supplies us with universal laws that can apply in any setting, not just a specific one. So like gravity, stuff like that gives us a general kind of understanding of how things move, even though there will be variation, like I mentioned before with like the river, still gravity is beyond the shadow of the doubt, or like electromagnetism, etc. Like, these are things that we can't really do away with, that are part of the very experience of nature. Or, as he'll get into, also laws of attraction, of the movement of matter, how matter can't be destroyed nor created, all that kind of good stuff that are universal principles within nature, yet are difficult to like prove or disprove in a kind of physical way, but are nevertheless true. So the reason he says that natural sciences are pure, like in the case of matter not being able to be destroyed or created, it's that idea does not work with our experience. Because in my experience, it seems like matter can be destroyed. You can destroy things. You could destroy a building. I don't know why I use such a violent example. If I were to eat a cake, it's like gone. It disappeared. The matter's gone. Or, whatever. You squeeze something down really small, it's gone. But the thing is, my experience is betraying me there, because we know that matter cannot be destroyed. It's just going to change composition. It might be, if it's something is squeezed, it might become tighter. And we're actually going to talk about this more. It'll form a black hole, which is something Kant didn't know about, because how was he supposed to know in the late 18th century? But it's something he will talk about. Now, this is why we have to rely on pure natural science that relies upon these laws that are not just about experience, because my experience is going to lie to me. My experiences tell me that matter can be destroyed or that matter can be created, but that's not true. So with this on our minds, let's start with matter, and then we're going to talk about space and time and movement, etc., etc. Another thing I keep saying, etc., etc. Wow. So to begin, we have to return to the categories that he talks about in the first critique in the Prolegomena, and that is the categories of quantity, quality, relation, modality, as simply as necessary possibilities or ways to apprehend things happening in the world, things that exist in the world. That is, we perceive something in terms of its quantity, in terms of its quality, size, shape, etc., its relation to other things, and its like direction. Does it have one? Is it moving? What is that like? So, and these will be the focus of each of the following chapters, where chapter 1 will take on quantity, which considers motion as a pure quantum in accordance with its composition, without any quality of the movable, and this can also be called pheronomy, but this is going to be chapter 1. Chapter 2 is going to look at quality in more detail, and quality refers to motion as belonging to the quality of matter under the name of an original moving force, and is therefore called dynamics. The third one is relation, and it considers matter with this quality as in relation to another through its own inherent motion, and is therefore called mechanics. And finally, modality, it considers matter's motion or rest merely in relation to the mode of representation or modality, and thus as appearance of the outer sense, therefore phenomenology. So that was quick. Let me just quickly summarize that. The 4 main chapters of the book are going to coincide, they're going to mirror 4 of the categories that he introduces in the Critique of Pure Reason, which we don't have to go back into there. You go listen to that, go listen to the Prolegomena, whatever. But they are quantity, quality, relation, and modality, also known respectively as pheronomy, which is also today called kinematics, the study of motion. The second is quality, also called dynamics. The third is relation, also called mechanics. And fourth, modality, which also is referred to as phenomenology. And as we go on here, we're going to start with quantity and work all the way to modality. Each one is going to go from less abstract, or from more abstract, to less abstract. Where the first one, quantity, we're just going to be talking about, in very abstract terms, what it means to measure movement. What does that tell us about a moving thing? What does it tell us about the space that it's in? Is it that the object moves or that space moves? So we're taking a very kind of generalized approach here. And then when we get to the end, modality, where he talks about phenomenology, it's just like relativity. It's like, how does my subjective position determine how I perceive a thing to be moving, and how that actually, in a sense, kind of constitutes its movement. And that puts us here into chapter 1, titled Metaphysical Foundations of Pheronomy, or quantity, or kinematics, as it's more popularly understood today. So he defines matter here as that which is movable in space. Easy definition. If something is movable, it is therefore matter, as opposed to something that's not movable. What is not movable? Well, that's a very good question. Is space movable? That's a very good question. Is there a totality of space? Like, if each space that you occupy, like the space in this room, and then outside of this room, my apartment, and outside of my little apartment, then the city that I'm in, then the country, then the Earth, then the solar system, then whatever, larger galaxy, then you keep going on and on and on. These are all like relative spaces that we need in order to measure anything in one of the smaller spaces. So perhaps there's a point when we arrive at the totality of all space. This is called absolute space, like the space that does not move, like the big sense of space that encapsulates everything. Perhaps that doesn't move, but we have no idea. So if space is movable, he calls that relative space. Whereas if it is not movable, it refers to the totality of space, and it is absolute space. And here we will just focus mostly on movement and direction, and not on their qualities, which we'll get into later. We're just going to talk about movement and direction in very abstract terms. Also, he's going to be talking, like, if you read this book, he has like these diagrams of like different mathematical equations and looking at different vectors and magnitudes and all that. It's all great. I'm going to try and distill it so I don't need to rely on like images, because I can't communicate that to you very well. So I'm going to distill it in a way that I think will make it still make sense. But that's kind of where we're going. That's where we're going here. Now, the reason that this is relevant is that we need to have and develop, this is something we probably just take for granted. Anyone who like studies, and this is what I think is really tragic about the sciences, is that there's little interest among prospective science students to dig into the history of these knowledges of because there's so much to learn that like they can't be taking up a ton of time with the history of like what people thought 300 years ago. But I think it's super interesting, and I think it's I think that it would give us a great way to, develop science for the future if there was an engagement with the science of the past. But I don't know. I'm not a scientist, of course, so there's probably a really good reason why they don't. I don't know. But he says that it's important for us to talk about space and movement in this way, in this kind of abstract way, because it is only by understanding what movement is that we can understand the comparison and the addition or subtraction of speeds. Because in order for us to do that, we need to have an agreement that two objects of the different size, different shape, at different places moving are at all relatable by virtue of them moving. So like there's something to be said about each of them in a kind of commonality by virtue of them moving. And if you've ever taken like physics, you'll probably know those annoying tests where it's like you're given a little diagram. You start at Billy's house and you drive 6 kilometers, like 4 miles, whatever, do the math, 6 kilometers north, and then 2 kilometers east. And then you got to figure out the, it's like the hypotenuse vector that you were driving, by going 6 kilometers north, 2 kilometers east. Like, what is I forget the term. It's like your net direction or something. Like, what direction could you draw in one line that would encapsulate those two other movements, the north and then the east? It is only by having an understanding that those two movements are comparable because of our understanding of what movement is that makes that equation possible. But when you learn about this stuff, you're not taught that. You're just taught this is how you do the equation, this is how you figure it out. And you aren't asking like, wait, what does make these things similar in order for allows us to like do this mathematical equation to them? And the added dimension here is that questions like those pretend as though any measurement of movement happens in a non-moving space, which is weird because we are always moving. On Earth, like the Earth is moving however fast it's moving. It's also rotating on its axis. We are in constant movement. We are never actually still. And so velocity is already kind of weird and out the window, but we're going to talk about all that. And really, again, like Kant was talking about this stuff. When I read this, I was like, I could not believe that he was already talking about this stuff back then. At least in, Europe. People in, the Middle East were talking about this stuff for thousands of years. But like in Europe, that this guy would have been talking about this is all right. So when something is moving, it is moving within relative space. Now we must postulate the existence of an absolute space that is not moving, because otherwise we wouldn't have the image or the possibility of thinking the idea of non-movement, because we're just like moving all the time. We need to believe that when something is moving, it is moving in relation to a non-moving object or space. When I move through the room, any room, it would be extremely disorienting for me if I was totally aware of how this room is moving on the Earth and how the Earth is moving through space. That would be weird. And we don't really do that very well. We exist by believing that the space we occupy is not moving. So we have to have some recourse to this speculated absolute space as that which is immovable and against which to measure the movement of relative space and to measure the movement of, like, how do we know the Earth is moving unless we have a relatively non-moving space, that is the solar system, that we can actually use against which to measure the movement of the Earth and the rotation of the Earth, which then we must do with the solar system, because we take a step out and it looks like, oh, the galaxy isn't moving, whatever the next step is, be kind to me, whatever. But we know that, and so then we use that as a reference point to measure the movement of the solar system. So we don't actually see these spaces moving. And so we have to rely upon a priori principles taken from experience that we've inferred and through our reason that we've come to, in order to make these claims about spaces moving and relying upon a relative non-movement that is itself only another relative movement, even though it appears like it's not moving because it's bigger, because it's a much larger vessel. And so therefore, like, I just want to make this really clear. Sorry if it's like if you've ever taken, I've seen the, I don't know why this is coming into my mind. I've seen the videos of like cruise ships, like the Disney cruise with like water slides on them, which scares me. Like the idea of going on a water slide that like looks like it's about to go out into the ocean spooks me a little bit. Not the point. But if you take one of those water slides, you're moving with the water within a slide that you perceive as not moving, but is really moving as it's like kind of tied to the ship. And you have no perception of that as you're moving through this slide. But then that ship, like compared to the Earth, might appear to like not be moving at all, or would appear to be moving, because you now have a bigger thing to compare it to. If you're looking out then at the ocean, you see that the ocean looks still, while it is the boat that is moving. So for motion to be perceived, we must acknowledge that the object in question occupies a point that traverses space, or, as with the Earth's rotation, it occupies one point but still it moves. So there are motions that stay in one place and continually return to a point. This is like a circular motion or oscillating motion, where it's always coming back to the same point. And motion that proceeds elsewhere is rectilinear and or curvilinear motion. This is like you shoot a basketball and it has like an arch and then it bounces away somewhere else. It's not returning to its point. So all these examples can be reduced to speed and direction. Direction is tricky because it could be said that as the world spins, for example, it looks in every direction around it, or it just moves west to east. Like, all of this relies upon like so much. So in order for us to have an idea of movement, we have to have an idea of speed as a pure idea and direction as a pure idea. But that is very difficult to do because we need human-made concepts to understand it, like the Earth's rotation, where we don't know that the Earth is rotating. And if you were to go to a spot on the Earth, like if you were to go to one of the poles, the North or South Pole, you're not really spinning up there. Like the Earth is not really spinning because that's like right on its axis. That's like, there's a point there when you're like right where the Earth is. And it's like, you're not really experiencing that full spin. You wouldn't be experiencing it anyways, but you know what I'm saying. Now for an object that moves through the world rectilinearly, like I shoot a basketball, it has a direction, it has a speed, and it is through those things that we're able to measure a kind of movement in its relation to a certain relative space. Now, with the spin of the Earth, it's a little bit different because doesn't look like it's really moving anywhere, and it doesn't really look like it has a direction, but it is moving. Now, the thing is, it is moving in every single direction. Like, how can we say that the Earth is moving from west to east, which is kind of how the world actually rotates, unless we have some kind of preconceived notion about what west and east are? But is the Earth really moving west to east? I mean, is there such thing as north, south, west, or east in space? No. Like, we look up at the stars at night and we think that's up, but we could very well reorient our minds to thinking that when you look up at the stars, you're actually looking down at the stars. It's a fun little experiment. If you're ever like outside looking at the stars, like really try to imagine you aren't looking up, but instead you're looking down. And it can produce this like vertiginous? It's like vertigo. It'll produce a weird feeling in you. So what this all tells us is that it's all a matter of perspective. Space and direction and speed and all that, they are not qualities of things in themselves. Because if you know anything about Kant, he's not interested in things in themselves. That's like, we can't know what that is. We can only know what things are by how we see them, perceive them, sense them. But instead, this is to point to the subjective form of our sensible intuition. That, in English words, what that means is looking at the ways in which the things we're looking at out there in the world are not just out there and we're discovering them. They are as much a product of our own minds insofar as our senses give us a certain image about that thing that might be different for a different animal, might be different for a different human, whatever. And so it is in that way that we constitute the object that we are therefore then investigating. This is the basis of phenomenology. The world shapes us, and we shape the world. Now, we'll talk about this more in the next chapter, but this does beg the question of rest. Is an object ever at rest? Because on Earth right now, nobody's at rest. The Earth is moving at a wild speed. We are technically, like relatively, it looks like we're moving quite fast. So here he provides a diagram to show in what case an object is ever at rest. So if there's an object, imagine the game Pong. If you're familiar with this old computer game, it's just like a little dot that bounces from one side of the computer screen to the other. And with that, the dot has to go, it's going at a constant speed. There's a point when it hits the wall and it changes direction. So the question is, did that ball rest at the side of the screen? And the answer is no. Kind of. It's kind of no. Even though technically its speed was measured by its constant motion in one direction and then immediately in the other direction. Now, what that implies is that they negate one another at some kind of moment where the thing is changing direction instead of proceeding in the direction it was once going in. But in order to maintain a constant movement in the opposite direction, it must at some point have passed through zero and then proceeded in the other direction. At least this is what it seems like, but that's not really the case. And this isn't even saying about the whole, like, well, the Pong is on the computer screen on Earth, so it's always moving. Like, we're putting that question aside for a moment. Now, in that case, it doesn't actually rest. At no point did the movement at any point just stop in any way. Now, the difference is like if you were to take a ball and throw it up to the sky. Now, it goes up and it comes back down. What you see there that is different is that there is a point when the ball will rest. It will rest at the apex, at its highest point before it comes back down. And that is because rest is achieved because it's not constant motion. It's not just one speed all the time, because that's what essentially betrays the idea that a constant motion thing can be at rest, because if it's truly constant motion, it's never at rest. If an object is accelerating and then decelerating, and then accelerating once again, what that tells us is that it is steadily approaching zero. So if I throw a ball up into the sky, gravity is working on it in such a way as to eventually arrive at zero. Then when it hits that point, it recommences its acceleration in the opposite direction. And so in that case, it can technically be at rest, even though, same thing, if you're on like a cruise ship, like if I'm throwing a ball up in the air, it looks like it's at rest. There's a point it stops. But if you're somebody on another boat watching this cruise ship, you're seeing this ball in the air, but it's moving not just up and down, but also in whatever direction the ship's moving. So you're seeing it from this other vantage point as always moving and therefore not in rest. So really all movement, it's not found in a thing in itself, but instead it is combined with the movement of a body and the space it traverses, but in the opposite direction. So if the space moved in the same direction, the body would be at rest. Now this is all like super abstract stuff. If I walk through my room, that is technically no different than saying that the room has been moving in a way to match my speed. So if, what would be a good example? If you're driving through a tunnel and the tunnel suddenly develops the ability to move, if the tunnel moves at the same speed as you, you're not moving. It's like you're not moving. It's like you're at rest. Now, in order for the tunnel to actually move, if the tunnel moved in the other direction at, let's say, the same speed that you're going, but in the opposite direction, you will then feel like you're going twice as fast. Or like a spaceship in space. If a spaceship is going through space, like the darkness of space, is it that the spaceship is moving or is space around it moving? Obviously, it's the spaceship that's moving. This isn't like a tricky. I'm not trying to sell you some Mr. Crowley type stuff here, but it's an important question because we are dealing with relative spaces. All spaces are relative. We can't ignore that as I move through my room, the room is in fact moving with the rotation of the earth. I don't really perceive it that way, but it is. And so this is a relevant factor as well, because insofar as objects can move, so too can spaces move, which is something worth factoring in. Now, something interesting happens when we try to add velocities together, or two speeds together. If I imagine something moving from point A to point B, and I want to add another to it, all I have done is put two same things side by side, and I haven't added to them at all. Like if I want it to go twice as fast, two velocities doesn't produce a faster velocity. Now, to imagine an increase with an addition, we must imagine one speed in absolute space and the other speed as the relative space moving opposite to it, like I said before in the case of the tunnel. So the speed of the object will only then be double. So let me try to present this another way. Let's figure out what happens with two motions in different directions. So to produce a new, perhaps diagonal direction. So a boat moving north while the current pushes it, it produces a direction that is neither north nor whatever direction it's moving. Let's say east again. It's a direction that's neither north nor east. By contrast, no such new direction would emerge with two boats going in different directions because they are both speaking to absolute space, even if it's really impossible to do that. But the boats think that they're just moving according to their own speed and will, and nothing else is really moving them or affecting them. But that's physically impossible. So with these two boats, I can't really produce a new vector or a new line that captures their similar direction because they aren't comparable. Both boats are going in totally different ways. However, if I was interested in looking at their actual real movement in relation to the relative movement of the ocean they're on, then I would be able to find each one of their respective actual movements through the world. Not just just looking at their speed as pretending as though it's an absolute speed, but taking it more broadly within the space that it's couched in. Another case would be two equal motions in opposite directions, where that tells us nothing. If two cars go past one another, it doesn't really tell us anything about adding their speeds or velocities or anything like that. But if we were to pretend or imagine as though there was even wind, for example, not the greatest example, but if a car is moving on a treadmill and the treadmill is moving in the opposite direction, which is kind of what happens when you move through space, then that means that you're probably not going to move a whole lot. That's when you actually see velocities canceling each other out. No velocities are being canceled out if two cars are approaching one another at the same speed. They're just two cars approaching one another at the same speed. You can't really get or produce a science or a mathematical formula from that. So we can therefore infer that there is an unintuitive connection between space and speed here. If a doubled speed is, in his words, a motion through which a doubled space is traversed in the same time, then two equal speeds can be combined in precisely the same way as two equal spaces. Because that's exactly what speed is. It's how far you go in a certain time. That's all that speed is. The kind of constant movement of that, not acceleration, which implies the change of that. But this tells us that, therefore, there is an intimate connection between speed and being able to measure and recognize it and space. So if you were to double the speed, it would be this. You could do the same thing as shrink the space in half. That would be the exact same thing. And so there's a fundamental connection here between speed and space that he really wants us to grapple with. Now, in experience, none of this is really obvious because we don't see space moving. We don't really perceive that. So we need the understanding for him. This is the part of our minds that works through what we are seeing in the world, what we experience, and asks okay, is that actually how the thing is? The size of the sun is not really an inch long. It's much larger than that. So we apply our understanding to kind of see through the illusions that have been created. And that puts us here into the second chapter, Metaphysical Foundations of Dynamics. So here he's going to move from the kind of abstract idea of space and its qualities to things actually moving in space. So as he said before, matter is that which is movable. But also, therefore, matter is matter and movable insofar as it is able to and does fill space. It also, quote unquote, moves as it resists other movables trying to enter that space. So a space without matter is empty. There's no matter there, it's an empty space. So matter does not fill space merely by existing in that space, but by exercising moving force, by either moving into space or offering equal movement against another movable object trying to take its space. So you can think of this in terms of like planets, where planets have an attractive force to them through gravity, where a planet is able to attract other smaller celestial bodies, other planets, stars, maybe not stars, or other big rocks around it. And that is because all matter all matter possesses attractive force. All matter pulls things towards it by virtue of it taking up space and therefore producing gravitational pull towards it. Now, because it does that, it also possesses the capacity to resist force, which is exactly why the moon does not crash into the earth. Because if there was just purely attractive force at play, that is, the earth being much larger attracting in the moon, or the sun attracting in the earth, then they would just collapse into one another. But the moon exercises its own repulsive force through matter. And it does, and then this is exactly what he's going to talk about in this chapter, is the kind of delicate balance between matter's attractive versus its kind of repulsive, to repulse things, to push things, whatever. Repulsive? Damn, what's the word? To push things away. We're going to get there, don't worry. So when an object is moving into a space, it is applying repulsive force. It is not attracting anything to it. It is expanding into it. Therefore, it is repulsing. It is pushing away anything else that might be around it. So when the Earth moves through its trajectory through the universe, it is doing so in a way where it's constantly pushing objects out of the way. We often don't see them. They end up being like comets that just like hit the Earth. And we think that the Earth was just sitting still and it kind of appears this way and the comet came in and hit us. When it's like, no. We are, through repulsive force and through what he calls elasticity, it is that the Earth is also moving into spaces, therefore repulsing like from itself and expanding into other spaces, that then pulls objects in through its own attractive force and then meets the repulsive force of other objects. Now, this is also on full display in like small, if you look through a microscope and you see little atoms bouncing around, or smaller than atoms, whatever, bouncing around. What they're doing is attracting and repulsing one another at that molecular level, which is what he talks about as well. So elasticity is that process by which matter expands out into the world. It is kind of repulsing things around it by virtue of that expansion. It pushes things away, but it's also pulling things towards it that are of the right size and, that can be pulled towards it. So he says that matter can be compressed to infinity, and this constitutes the opposite of elasticity. If elasticity through repulsive force is the act of expanding outwards, then its opposite is compression. To compress, that is, to take matter and squeeze it together so as to eliminate as much of the empty space between each atom, between each bit of matter, as can possibly be squeezed together. And this is what happens if an object meets an expanding, repulsing force, but has nowhere else to go. So an object can be compressed and compressed and compressed, but it can never actually be penetrated by other matter. No matter can penetrate other matter, because that can't happen, apparently. I don't know. For physicists in the room, I'm sure there's some like quantum thing that would prove all this wrong. Lay it out for us. What's most important here is the way in which Kant is just using his philosophical approach to understand physics. And it's really good, especially for the time. So when an object or when matter is compressed, it is experiencing relative penetrability. Something is working on it that is causing it to move. But you will arrive at absolute impenetrability when then there's no empty space left, and the matter can no longer be penetrated, can no longer be exploited. Now, at the time, he had no idea about black holes. No one did. I think there was like one kind of idea that maybe there was such a thing as a black hole, where he just says here that a thing can be compressed just to this point, and then he doesn't say what will happen because no one knew. But it creates like a black hole. It's like an object of extreme density that has eliminated all the empty space within it. Extremely dense, very heavy, very small relative to other things. And by virtue of that, it produces like a phenomenal natural wonder in the form of a black hole. Now, it is so dense that it exercises a ton of attractive force where it pulls things within it and they can't get out. The repulsive forces of those objects, of the matter that's pulled in, is not strong enough to escape. So it's just stuck in there. So again, but he was writing at a time when they didn't know a lot of this stuff, didn't know about black holes. He also says that as an object, all objects are divisible, or all matter is divisible to infinity, at least mathematically. But he didn't really know about the possibility of the splitting the atom or what that would mean and the questions that would be raised from that. If there's a point, because I don't know the answer to this, physics nerds, you let me know. But like, what happens if you split this? Like, can an atom be further split? Like, it's been split in two, then can you split that half and then that half and then that half, and then will there be a point when there's no more splitting going on, when it disappears? Because the matter hasn't disappeared per se, but I don't know. You know what I'm saying? I don't know. I don't know. Whatever. Now, all of this is only speculation, that things can be divided to infinity mathematically. And therefore, this is potentially a quality of things in themselves. Like, we don't know. Or at least at the time he didn't know. Physics nerds, you let me know. Have we figured this out? Can you divide to infinity? What's that like? So in space and in our senses, matter is not divisible to infinity. Or the assumption of matter's division in space implies a connection between space and matter that doesn't truly exist. Nominally, then, that is in the noumenal world, things may be comprised of infinite parts. Phenomenally, however, we only apprehend the possibilities of division in the act of division itself. And therefore, so the parts of the phenomenal world are products of sensible faculties. We see things as composite, as never total. So there might be a point when we divide and divide and divide where we can no longer divide anymore. And that might be a thing's essence. It's kind of soul. I'm just doing bad metaphysics here, but like, let's say that's its soul. That is a point that it can no longer be divided. But to humans, things don't seem that way. I mean, people experiencing the world, it's like, yeah, maybe that can be divided. I don't know. Like, perhaps, maybe it can't. I don't know. What do people know? What does it look like to people? Probably not that you can divide an atom. Like, it probably, especially in the late 18th century, they were probably like, you're not going to get any smaller than that. You break a pencil a couple of times and then it's like, well, that's it. It's not going any further. So all matter exercises both repulsive and attractive forces, where physical contact may begin before contact insofar as matter's forces may act upon another thing. Like in the case of the moon. Like, the moon and the earth are enacting forces on one another, but they're not doing so because they have ever come into contact. Maybe they did at one point. I don't know. It's just the moon is a satellite, isn't it? It's a conspiracy theory thing. It's a conspiracy. The moon isn't real. Now, physical contact is the interaction of repulsive forces at the common boundary of two matters. That is what's happening when things contact one another. They are exercising their efforts to expand their own repulsive forces, and those repulsive forces are meeting, and also the repulsive forces of their attractions are meeting at some point on both of those matters. But that does take a kind of agreement as to what that all parts of a thing comprise that thing. Like if the moon were to make contact with the Earth, would that, like, what part of the Earth would it touch? And there will be a point when it's like infinitely close and hasn't yet touched, yet still it's decimated everything on Earth. But like that point there, does that stand in for the entirety of the Earth? Maybe. Is it just a point? Is it the Earth itself? Who knows? Like, what is that? What is going on there? So he calls these things that is attractive and repulsive forces, he calls them foundational forces. And he kind of talks about gravity. He seems to get it, like what gravity's role here. I don't really know how much he knew about like the bending of space-time and all that stuff. But he seemed to kind of get it. I mean, we hadn't had Einstein yet. But that's exactly where his mind goes with all this stuff and with his own philosophical approach. That's where it takes him. So with all this, we can see that property and weight are comprehensible a priori, whereas contact is not. That is things, and things are always movable. That is matter is that which is movable. And movable things possess certain properties and weights that will determine and that will play a part in their foundational a priori forces of either attraction or repulsion based on their weight, which is what happens in the universe. Like a heavier star and a more dense planet is going to have more attractive force a priori than a less dense one. It's just as simple as that. And these are the things that excite him about science, about physical science, about natural science, because it is by elucidating these fundamental forces such as these that we may develop a natural philosophical science, or natural science of philosophy, through metaphysical inquiry that is informed by, but ultimately exceeds, experience as a priori qualities. And it's interesting too, like, and this is one of the tragedies of the way in which academia has split up so many different fields, is like there was a time when people who studied astronomy were also studying philosophy, were also studying geometry, were also studying languages. Like education meant it was wide. You learned a lot, and it was part of your whole experience. Not like here now where it's like, oh God, you got to take the mandatory courses and something you're not interested in. That's tragic. That sucks. But I really wish that like there was a more holistic, broad, wide approach to education in like a deliberate way. Not like I'm here to study engineering and that is all. Like what? No, we should all be learning music too. Universal language. Come on, we gotta learn this stuff. And that puts us here into chapter 3, Metaphysical Foundations of Mechanics. And we're almost at the end here. We're almost at the end of the book because it wraps up quickly and there are points when it's just kind of repetitive, but short book too. Mechanics takes these dynamical properties, that is the properties of movement, attraction, repulsion, as a given and explores how they actually work from one object to the next. So we're still kind of abstract. We're talking about the natural movements of things, how they attract, repulse. But now we're going to ask, like, what actually happens when one moving body acts on another? So to figure out an object's momentum demands calculating its mass, how heavy it is, and its velocity, its speed, and multiplying those things, where force is equal to mass times velocity, I guess. So mass and velocity have an interesting relationship. All matter moves, and all matter is divisible into smaller parts. So movement actually gives matter coherence in a uniform body as all its parts move together. That is what allows us to see it as moving and gives it a kind of totality. So when you see a runner moving, you aren't saying, wow, that leg is moving really fast. No one would say that. Even though it is true, you'd say that person is moving very fast. When a thing moves, it means that its entire mass and all of its matter is in a kind of harmonious direction that gives it its shape in the way that there's uniform movement across all of its variations. So this is what separates mechanics from dynamics. Dynamics, what we just discussed, because we aren't anymore focusing on matter's innate repulsive or attractive forces, but we're looking actually at things as they move. So some of the laws of mechanics that Kant supplies us, he gives us a few different laws of mechanics that he takes partly from Galileo, Newton, I guess. Leibniz, I think, would have had a little influence on him, especially, I think he mentions the calculus stuff and whatever. But these are Kant's 3 laws of mechanics. The first one, matter cannot be destroyed nor created. Great. Perfect. Awesome. Number 2, changes in matter are due to external causes. And that is because all matter is lifeless. It doesn't have a will of its own. Like matter, if we're matter qua matter, as just matter, doesn't have a will and therefore cannot determine its own movement, its own destiny in the world. It only operates by having something else operate against it. And it's all like reserve energy from the Big Bang, or like the energy stored within the entire universe, where there are always things moving from its inception. It's just like hence one of the seductive elements of the Big Bang theory is like it was a great amount of energy, extended this energy into lots of different objects and sent them out into space. And now they're just banging against one another, and they're extending energy and passing energy from one thing to the next. And then his third law of mechanics is that every single action produces an equal and opposite reaction. We have all heard of that before. Action is equal to reaction. He doesn't call this a transference of motion. He says this is instead a kind of communication. He says it's a communication of motion because no object simply acts on another. That is an object that collides with another because the other's object's own dynamical force of repulsion and attraction. It's not as though there's just like an object sitting there still and then something comes and runs into it and transfers its energy. Because that object that got hit, like in the case of the Earth and a comet I mentioned earlier, the Earth is moving too, the comet is moving, and there's this kind of relationship, this kind of communication between their primary forces acting in various ways in that moment, where the comet is enacting attractive force that it's not very strong because it's just a comet, but it's enacting repulsive force as it's moving toward the Earth that is pulling it in while also repulsing it in its own ways. But of course, we know what the outcome will be because certain of those forces outweigh the others. Now, these 3 laws, he also calls them, also have a different name. That matter can neither be destroyed nor created, he calls this self-subsistence. That is, matter continuing itself. The second one, that changes in matter are due to external causes. He calls this inertia, like a thing at rest, that type of thing. And third, but nothing can ever really be at rest, but you know what I mean. The third, in the communication of motion, he also calls this the reaction of matters. And that puts us here into the 4th and final chapter, the metaphysical foundations of phenomenology. So matter is only movable insofar as it is an object of experience. And I remember a philosophy teacher I had years ago, Irini, great prof. She used to put it this way. She was like, it's difficult to imagine, in her accent and her way of speaking, very difficult to imagine, but with the end of humanity will come the end of the universe. And it took me a long time to really understand what that meant. And it's because the universe as we know it is only given to us through our specific senses. Who knows how a dog would perceive the universe? Or a bat, or another alien species somewhere else in the universe. Who knows how they perceive this stuff? And so all of these questions that we've been talking about so far have pretended as though there wasn't, like, the factor of human observation was not at play. We were just talking about these things in kind of pure ways, which is nevertheless true, but we can't forget that the only way we were able to talk about these things was because we have a mutual understanding of what, like, movement is, what speed is, direction, etc. And we are able to have such experiences of things in the world because we rely upon, without them being made totally clear, certain ideas, like the idea of absolute space, like the idea of the comparison of velocities, like the idea of repulsion and attraction, of gravity. These things are required for us to have an understanding of things existing in the world, and we harbor within us the capacities with our reason and our understanding to be told what they are like once, and we kind of get it, which isn't that isn't like a miraculous thing in itself. I think it's kind of cool, but we kind of get it, and it makes sense, and then it's from there that we're able to better understand the world, to clarify in our minds what parts of our experience are wrong, like the sun looks really small but it's really huge, that kind of thing. So we, as humans, we have like this reservoir of knowledge and clarity that is given to us only by having gone through the obscurity of experience and how experience can lead us astray. But we have these clarifying mechanisms in our mind that help us make sense of other things in the world that might otherwise we may not have been able to make sense of. And he concludes by highlighting that all of this depends upon necessary yet kind of impossible things like absolute space. To understand movement at all, we have to imply as though a thing is moving without anything around it moving, as though it exists within an absolute space that is itself not moving. But all space is really moving. So we have to have, we are just using this kind of synthetic a priori just fiction that is nevertheless necessary in order for us to understand movement and space at all. Otherwise, we would just always perceive and understand things moving relative to others, which is important, but that's kind of poses a problem when we're trying to figure out a thing's velocity. And also the impossibility of empty space, which is often used to understand something moving into something else. But there's no such thing, like there's matter everywhere. Like on Earth, there's atoms or whatever. In space, I don't know. The ether? Whatever. But yeah, that's pretty much it. It's a interesting text. I mean, not necessarily for its physics. I think it is for that. But just in the way that Kant's philosophy informs his ability to do physics in this way, which I think is super interesting. But yeah, if there's anything I got wrong, anything I excluded, I'd love to hear about it. If you like what I did, you can like, share, subscribe, tell your friends, who knows, they might like this. Maybe they won't. There's only one way to find out, though. Let them know. But yeah, hope you like what I did, and I'll catch you next time for some more German idealism, probably. Not sure what that'll be. We'll see, though. I'll figure it out. Anyways, peace out, y'all.